We looked at various means of solving differential equations. We've looked at analytical ways of solving them. We've looked at numerical ways of solving them. And we've looked at power series ways of solving them. And among the most powerful methods of solving differential equations are transformations. And the two most prominent transformations are the Laplace transform and the Fourier transform. Here we'll be talking about the Laplace transform. So generally there are these mathematical concepts called integral transforms, okay? And so what an integral transform is, and the integral transform that we're going to be mainly concerned with are ones that are unbounded on the interval of integration 0 to infinity, okay, inclusive of 0 there, with ft defined for that interval. And we also have the concept of the kernel, okay, which is in the integral transform. So here's the integral transform, okay? So what you do is you'll take this function, which you're going to transform, using this kernel, and you'll integrate this from 0 to infinity, right? It's an improper integral. And the way you do improper integrals is you integrate from the lower bound, so the finite lower bound 0 to b. Okay, then you'll have an expression that depends on b, and then you take the integral, the limit as b goes to infinity. If this converges, then the integral is called convergent, otherwise it's called divergent. And something to keep in mind here is, f is considered a function of t here. The variable of integration is t, and this kernel is a function of two variables, s and t. So what happens when you integrate through the variable t, right? What happens if you take, like, say, just an arbitrary integral of x and you have a lower and upper bound? You'll just get a number, right? Well, here, that will happen to the t variable, and so what you'll be left with is an expression of s. And so this final expression, okay, will be some function of s there. We integrated away t. Okay, so that's just this remark over here. And we're going to be mainly concerned with an integral transform called the Laplace transform, where the kernel is this e to the st. Okay, so that's the kernel, and this is called the Laplace transform. So more formally, let f be a function defined on this interval, then the function f, okay, defined by f of s. Notice it's a function of s. Is this improper integral from 0 to infinity with the kernel e to the minus st times ft, and it's called the Laplace transform of f. F is what's being transformed, the function. The domain of fs is the set of values of s for which the improper integral converges. So where this converges, that's going to be the domain of now this function here, which is the Laplace transform of lowercase f, okay? F of s is often denoted, so we'll represent f of s, the Laplace transform of lowercase f, as this L with f inside there. So that's the definition of the Laplace transform, and we want to apply. Okay, so whenever you solve for the Laplace transform of a function using the definition, then you actually carry out this integral. Okay, that's what's meant by using the definition. So let's use the definition to compute the Laplace transform of the constant function 1. So here we have a Laplace transform of 1. We plug in, instead of an f, we have a 1 right there. And you taking this improper integral of e to the minus st with respect to t. So how do you treat s here? Just as a constant. Okay, so we're treating s as a constant when we're integrating with respect to t. So we integrate, and we get just, again, s is treated as a constant, so you get this 1 over s there for the integral of the exponential. and our bounds are from 0 to b, and we're going to take that bound to infinity. So when we do that, we get this expression here when we plug in the bounds. And when we take the limit as b goes to infinity, this term goes to 0, okay? And we just get 1 over s, which is what's left. This works for any s strictly greater than 0. And we typically are not going to be writing, if you're interested in learning more about improper integrals, in the Calc 2 series that I have, I discuss it more in depth. But we'll omit this language of limit b as b goes to infinity and just plug 1 to infinity there. But it's understood that you're taking actually the bounds from 0 to b and then taking b to infinity. Okay, so for example, in this example here, we want to find the Laplace transform of t. So we do the similar steps, and this time we have a t there where we plug that in for f. And well, how do we do this integral? We do it by parts. So you want to transfer the derivative from this expression to the t, okay? And you do that by paying the price of a boundary term and a minus sign, which you don't see here because we have a minus minus. It turns into a plus. And notice what we end up with, 0 plus 1 over s. And this guy here, well, that's exactly this, okay? So that's just the Laplace transform of 1. Rather than compute it all over again, we just plug in 1 over s, which is what the Laplace transform of 1 is. We have this 1 over s multiplying it, we get 1 over s squared. And again, this will work for any s strictly greater than 0. If s equaled 0 or is less than 0 in either one of these, then what you're going to get is that this becomes unbounded, okay? So if s was negative here, then overall this is positive, and this term here will be, e going to e to the power infinity, in air quotes there, of course, because infinity is not a number, but this is divergent, okay, when s is equal to 0 or less. And likewise, this integral will be divergent if s is negative or equal to 0. Also, if you're interested in integration by parts, then I also encourage you to take a look at the videos that I made with regards to integration by parts in the Calc 2 series. We won't be spending much time here with regards to that. So let's continue using the definition to compute, this time, exponential functions, okay? So L of the exponential function e to the minus 3t. Again, we plug in e to the minus 3t there. This is from our Laplace transform. And we get this expression when we use the laws with regards to exponents. And this integral will converge whenever s plus 3 is strictly greater than 0, or s is strictly greater than negative 3. And you just do the standard computations there, pretending pretending s is a constant. And notice here, when you plug in the bounds, you plug them in for t, not s, because s is treated as a constant. So you plug them in for t, and you get that expression there. We do this similar thing for e to the 5t, except now we have this. And so we need s minus 5 is strictly greater than 0, or s is greater than 5, and we get a similar expression there. What about trigonometric functions? Well, let's do one. Here we're going to plug in sine 2t. And, you'll probably recall from Calc 2 that you're going to have to do this using two integration by parts. So the first integration by parts gives us this boundary term and this expression. Then we do another integration by parts, resulting in this boundary term. And so this 2 over s is multiplying This expression here will be 0, and so this 2 over s is multiplying what's the integration by parts due to this. So that you're getting this boundary term, okay, and this is the non-boundary term in the integration by parts. And there goes the minus sign. So distributing the 2 over s, you'll get, once you plug this in here, plugging in the infinity into here, that's going to give you 0, but you could plug in 0 into this. The cosine of 0 is 1, and this is going to, e to the 0 is 1, and so you'll get a minus sign there, but minus a negative is a plus. And so you get 1 over s from this boundary term there, and that's why you have 2 over s squared there. But anyway, once you carry this out, notice you're back to, what is this? This is exactly what we started with. Okay, this is exactly the same thing we started with. And so you're left with this expression. Now what you could do is this standard trick from Calc 2 with integration by parts, where you just solve now for the Laplace transform of sine 2t, basically solving for this integral algebraically. So we're going to move this to the other side, okay, and we get this expression here. We factor out what we want to solve for, and we get that right there. And we divide by this term to obtain this. Okay, and we now have our Laplace transform of sine 2t. And s must be strictly greater than 0 for this to work out. Okay, you see that because of these terms here, the boundary terms. Otherwise, you'll get divergence, just as we've grown accustomed to seeing. So when I said this goes to 0 at infinity, I should be careful and say that that occurs when s is strictly greater than 0, which is what gives us our domain for s. Well, when we were carrying this out, notice that after the first integration by parts, we have this. Okay, so we could relate, and what is this? This is the Laplace transform of cosine 2t. So why don't we use that fact and this equation to get L cosine of t, the Laplace transform of cosine t. So this expression here could be written this way, okay, because again, this is 0 when s is strictly greater than 0. And we then just solve for the Laplace transform of cosine t, and we obtain that right there with this domain. So an important theorem here is the linearity of the Laplace transform. Laplace transformations are linear. Okay, and what does that mean? More formally, suppose the functions f and g possess Laplace transform for s strictly greater than c1 and s strictly greater than c2 respectively. So for f it's this, and for g it's this. And we're going to take the max of c1 or c2. Okay, so whichever one is the maximum there, we're going to take that and we're going to call that c. And we're going to let alpha and beta be constants in the reals, so real constants. Then the Laplace transform of this expression is equal to this. Okay, in other words, the Laplace transform of the sums is equal to the sums of the Laplace transforms. Okay, and this also applies to scalar functions. The Laplace transform of alpha times f is equal to alpha times the Laplace transform of f. The Laplace transform commutes with scalar multiplication and summation. Okay, and it'll converge for s strictly greater than c, which recall is the greater of the two. That's why we took the max of those two. So let's see how this theorem could be helpful, and it is really helpful, unless you appreciate computing Laplace transforms always from the definition and taking the improper integral. Let's look at sinh t, okay, hyperbolic sine. So Laplace transform of that, well, what is hyperbolic sine? It's this function here, okay? It's e to the t minus e to the negative t over 2. by linearity, we could, quote, distribute this L. And so when we do that, we get this over here, okay? Since Laplace transform commutes with sums and scalar multiplication. And we know the Laplace transform of e to the t and e to the minus t, okay? It's these, okay? We've done other numbers, but it's extremely similar. And notice that this here converges when s is strictly greater than 1, and this converges when s is strictly greater than negative 1. Okay, so this has a larger domain, if you will. But nevertheless, we take the smaller of the two domains or the larger of the two lower bounds. Okay, that's the same thing, saying the same thing. So s is strictly greater than 1 here for the domain, and when we combine these two, we get 1 over s squared minus 1. Of course, we have that half there. So we'll get this expression there for sinh t. We may also use trigonometric rules. So if we want to find the Laplace transform of cosine squared, well, what is cosine squared? Using the half angle identity, we could write cosine squared as this. And then using linearity, we distribute that L, and we get this expression. Well, we've already found the Laplace transform of cosine 2t. That's this. And we've already found the Laplace transform of 1. We've computed it from the definition. And so we end up with that expression for cosine squared t. See how linearity really helped us out instead of solving a stubborn integral. We could get all sorts of formulas and prove the following identities using induction. So for example, we have this here. Well, this could be used, we calculated the Laplace transform of 1 and of t. And what about like t to the 100, right? It'd be nice to have a formula. Well, from this expression here, which again could be proven by induction, then we could actually compute all of these, okay? And we have the following theorem for some basic Laplace transforms of some basic functions. So L of 1, we've computed that from the definitions, 1 over s. L of t to the power n, again using this formula here, and starting with this step here, or of L of t, you could get this formula there for n being 1, 2, 3 natural numbers greater than 0. L of an exponential is this. L of sine kt, okay, is this. Cosine kt is that, okay. And so you get these, basic. There are, of course, a lot more complicated tables. But here are some basic Laplace transforms to work with. And along with the property of linearity, could be used to solve get the Laplace transform for a lot of different functions.